Now we'll make the orbital diagram for it. It's very easy and very you can say a tricky task. So just look at the board. So suppose I need to write the if I say I need to draw the molecular orbital diagram for hydrogen molecule. So my first step is that I need to calculate the total number of electron possessed in that molecule. So this is what I have done for you. Atomic number 1 into 2. So that means how many electrons? 2 electrons. Now what I will do is I will write the configuration. It is sigma 1 is 2, only sigma 1 is 2 we are left, because 1 into 2 2. So there is no other, you can say, electronic configuration. So what we will be doing, we will be making one box here, this is sigma 1s and this is sigma star 1s. And these sides are indicating my atomic orbitals. That means atomic orbital for hydrogen A, let's say, atomic orbital for hydrogen B. So if you write the this thing configuration for atom, so it will come out to be 1s1, right. So I will be writing the atomic orbital combination this thing here, and now I will be just writing in a molecule. So when I will write in a molecule, I will see that it occupies 2 electrons and it is left vacant. So what I will do is I will try to make a box like this. So this is my energy level diagram for hydrogen molecule. Now let's make it for oxygen. So first is to write the electronic configuration. Sigma 1 is 2, sigma star 1 is 2, sigma 2 is 2, sigma star 2 is 2, sigma 2p z2, pi 2px is equal to pi 2py. Let's count 2, 4, 6, 8, 10, 11, 12, 13, 14, and we have 15 and 16. So now we'll be drawing a diagram now, right. So let's make a box here. Let's say this is 1s, sigma star 1s and sigma star 1s, sigma 1s, sigma star 1s, and this is my atomic orbitals of oxygen atom, 1s, 1s. Let's join them. Now make another one, sigma 2s. As you wrote the configuration, you need to draw the boxes like that. And this is my atomic orbital 2s, this is my atomic orbital 2s. I will just join it. Now I have the 2pz also. So let's draw 2pz. Sigma 2pz, pi 2px is equal to pi 2py. So I need to divide into two parts because they possess the same energy. Then I have is again anti-bonding 2px is equal to anti-bonding 2py. I need to like this. And I can also write sigma star 2pz, and this is my atomic orbital for oxygen atom, that is my 2p. So this is how you need to draw. I will just join it again. Right. Now start filling the electrons. As I told you, we fill electron according to the same rules, so we need to follow that. First we will write the atomic orbital configuration. So it is 8, 1s2, 2s2, 2p 3, sorry 2p 4, 4, 5, 6, 7, 8. Now these are indicating my atomic orbitals, right, and this is my molecular orbital. So I need to fill the atomic orbitals first. So let me fill 1s2, and again for the other one again same 1s2, because both the atoms will having the same configuration. 2s again 2, again 2, 2p is 4, 1, 2, 3 and 4, 1, 2, 3 and 4. Right. So my atomic orbitals are already filled. I need to fill my molecular orbitals now, and the electronic configuration is something this which I wrote. So let's say that in bonding sigma 1s2 there is 2 electrons. Let's put 2. Anti-bonding also possesses 2 electrons. So this is completed. Now for 2s, bonding again 2, anti-bonding again 2, this is completed. And this is now 2pz possesses 2 electrons, as you can see here, and these are again 2, 1, 1, 2 and 2. I am just doing in a way that the pairing take place until each orbital with the similar energy is singly filled. So likewise, like it has 4, that's why I didn't wrote like this. You also make a habit not to do like this, just make it singly filled first, then pair up. Then pi 2px in this 1 and 1 electron. So this is my molecular orbital diagram for oxygen molecule. Now let's draw a molecular orbital diagram for nitrogen. So you know that first what we need to do is we need to write the electronic configuration. Sigma 1 is 2, sigma star 1 is 2, sigma 2 is 2, sigma star 2 is 2. Now here the order just gets changed. We know that 2pz will come at the back of pi 2px and pi 2py. So it is pi 2px, pi 2py, sigma 2pz. So let's fill 2, 4, 6, 8, 9, 10, 11, 12, 13, 14. That's it. No anti-bonding, no electron in the anti-bonding one. So let's draw a diagram now. Again, I'll write the for an atom also. 1 is 2, 2 is 2, 2p, 3. Right. So now again we'll make this kind of boxes. Sigma 1s, sigma star 1s, and here comes my atomic orbitals. I'll join them like this. Now I'll fill for the 2s one again, sigma 2s, sigma star 2s, this is my atomic orbital 2s and 2s. I'll join with the multicolored lights. Let's make it colorful. Right. Now my 2p, you need to see that here there's a difference, right? So likewise you need to draw the orbital like the same orbitals in this case also. So it is pi 2px equal to pi 2py, I put the line. Then I have sigma 2pz, and my anti-bondings are vacant actually, but the method of writing it is same. These are my anti-bonding, and these are my atomic orbitals 2p. I'll draw the orbitals also. Right, so just we'll join them. Right. So now I will fill the electrons, right. So this let's fill the atomic orbitals first. 1 is 2, I'll put 2 electrons here, same here also. 2 is 2, again same here, same here. 2p 3, so 1, 2 and 3, again 1, 2 and 3. Right. Now I will just change the spin, because when they need to combine they will be opposite spin. Let's put like this. Now we'll start filling the molecular orbital. So as you can see, it is sigma 1 is 2. So we'll fill sigma 1 is 2, sigma star 1 is 2, again this, sigma 2 is 2, again this, asterisk sign again, this 4 electrons, and this is 2, and these are vacant. So no need to think for that, like if any orbitals remain vacant, it's none of your business. You just fill the orbitals accordingly like you wrote the electronic configuration. So this is my energy level diagram or molecular orbital diagram for nitrogen molecule. So this is how you need to draw the orbital diagrams. So first is that write the number of total electrons in a molecule, write the configuration for the molecular orbital, and also write the configuration for the atomic orbitals, because you need that, because we need to fill these corner ones with the configuration of the atomic orbitals, because we need to show that how actually they are combining with each other, right. So these are the energy molecular orbital diagram. So now due to we get many informations regarding to many properties of the molecule also are indicated by this diagram. So let's look at that properties. First property is bond order. First property is bond order. Bond order actually indicates the number of bonds which are present in a molecule. That means whether there is a single bond, whether there is double bond, whether there is triple bond. So that is actually indicated by bond order. Now how we calculate the bond order? It is actually bonding electrons minus anti-bonding electrons divided by 2. bonding electrons minus anti-bonding electrons divided by 2. So let's apply this formula to 3 of them in order to find the bond order, right. So in here, if I apply this formula, I need to find bond order, and I write bonding minus anti-bonding divided by 2. How many bonding electrons? Because here in this, like when you are calculating the bond order, you don't need to look for the molecular orbital diagram. By just looking at the configuration which you wrote for the molecular orbitals, you can just see that and can calculate the bonding and the anti-bonding electrons. So how many bonding? 2. And anti-bonding? 0. You have to divide it by 2. So what result do you get? 1. And it's absolutely right, because in hydrogen molecule, when we form, there is only a single bond. Right. So likewise, you need to calculate the bond order. Let's calculate for O2. Again, you need to apply a same formula. Bonding minus anti-bonding divided by 2. So let's count the bonding ones. 2, 4, 6, 8, 10. So these are my bonding ones. Now calculate the anti-bonding, that is with the asterisk sign. 2, 4, 5 and 6. So it comes out to be 2, and we already know that when an oxygen molecule is formed, there is a double bond formed. We already did when we were drawing the covalent bond. So here you can see that bond order is just matching up with the number of bonds. So it just indicates that how many bonds are present in a molecule. Let's see it for nitrogen molecule as well. Bonding minus anti-bonding divided by 2. Let's count the bonding ones. 2, 4, 6, 8 and 10. And anti-bonding 2, 4. So it comes out to be 3, and it's also absolutely right, because we know that in nitrogen molecule there is a triple bond. So likewise, when you are drawing the energy level diagram, you can calculate the bond order. And you know that bond order actually give an information about the bond length also, because bond order is inversely proportional to bond length. More is the bond order, less is the bond length, because more stronger is the bond. Like you saw in this, that it is a single bond, it is a double bond, and it is a triple bond, right. So in which the bond order is high? Obviously in this. And in which the bond length is shorter? Obviously in this, because they are more closely packed. As you can see, there are 3 bonds present, and in comparison to that, here is only 1 bond and here is only 2 bonds. So this is my second information, that we get the information related to bond length. Third information we get according to bond dissociation energy. That means energy which is needed to break the bond. So what happens is, it is actually directly proportional to the bond dissociation energy. More is the bond order, stronger is the bond, more is the energy required to break it. So as you saw that in the, when we compare these 3 molecules, it has the highest bond order and the least bond length. But when we talk of bond dissociation energy, obviously the bond dissociation energy is going to be greater, because here you need to break 3 bonds, and in comparison to that, here you need to break only 2 bonds, and here you need to break only 1 bond. So obviously bond dissociation energy will be higher for this, right. The fourth information which is revealed by these diagram is the magnetic character. Magnetic character implies that whether the given molecule is being attracted by the magnet or it is not attracted by the magnet. So likewise, we divide them in 2 categories, that is diamagnetic and paramagnetic. We divide these molecules into diamagnetic and paramagnetic. Diamagnetic are actually repelled by the magnet, right? And paramagnetic are attracted by the magnet. Now how you will come to know that which molecule is diamagnetic and which molecule is paramagnetic? It is very simple. You just need to look at the configuration of the molecular orbitals, and by looking at that you can just find out that whether the molecule is diamagnetic or paramagnetic. Like see in this hydrogen molecule, you get to see that here there is no unpaired electron left. So when there is no unpaired electron, that means the substance is diamagnetic. This kind of substance, when kept in a magnetic field, it will be repelled by the magnet. Now in case of oxygen, let's focus on that. The configuration, 2 filled, 2 again, 2 all are filled. But pi star 2px and pi star 2py are having only one electrons. That means they are having the unpaired electron. So this is something called as paramagnetic. So that means if we talk about the magnetic character of oxygen, it is paramagnetic. It is going to be attracted by the magnet when it is exposed to a magnetic field. Likewise, if you see for nitrogen, so as you can see, all the shells are completely filled. They are having 2 electrons, no unpaired electron. And when there is no unpaired electron, we know that the molecule is diamagnetic. It will be repelled as the hydrogen was repelling in a magnetic field. Similarly, it will be repelled. So, like if you get a question like this, like if somebody asks you to draw a molecular orbital diagram, first you need to calculate the total number of valence electron, then write the configuration for the atomic orbital, then for the molecular orbital, arrange them in this order as I did for you, start filling them, and after filling them just came to the write the conclusion about indicate these 4 properties: bond order, bond length, bond dissociation energy, and even comment on the magnetic character. So this is very simple way, and if you get an ion, like if you get this kind of thing, if you get this kind of molecule like to draw energy level, it's very simple and it's almost same. What you need to do is you need to subtract this much number, like if it is negative you need to add, if it is positive you need to subtract from the total number of valence electron, otherwise everything remains same. Everything remains same, but there will be difference in the configuration, there will be difference in the filling, there will be difference in the bond order, because the bonding and anti-bonding will get shuffled out, right? So this is what you need to focus. If there is a charge, you need to, like if there is a positive charge, you need to subtract that number of electrons. If there is a negative charge, you need to add that much number of electrons. That's it, right? So this is our molecular orbital diagram, and by doing this we finish this chapter. So just try to make these diagrams, try to do the overlappings, just make well versed with the kind of energy involvement and all.